particular, if you have attended a previous version of this talk, you might find already some changes. But let us start. So, okay, so the title of my talk contains the words partially ordered set. So let me fix some notation. So let P be a finite poset such that first P is bounded, and let me denote 0 hat, the minimum of P, and 1 hat, the maximum of P. So by saying that P is bounded, I claim that there is a single element that is the minimum and a single element that is the maximum, and that P is graded. So I have a function rho that goes from P to the set of non-negative integers given by rho of S, where S is some element in the poset, equals to the size of any maximal chain starting at 0 and ending at S. So being graded means that this row is well defined. So all the maximal chains have the same length whenever you fix the top. In full generality, we will not require the poset to be graded, and we will actually not require the poset to be finite, but just locally finite. But for the purposes of this talk, I think it's enough to focus in these assumptions, because yeah, there are some technicalities that arise when one works with a weak rank function and locally finite posets, but everything is essentially the same. Let me say that. So once we have a poset, we can consider what is known as the incidence algebra of the poset over the ring of polynomials in a single variable, let's say. Let me write this in case you're not familiar with this notion. So the incidence algebra of P over the ring of polynomials with integer coefficients and variable x is the free set x module over the set of closed intervals of P, where the product that will turn this into an algebra is given by, so A times B. So I have to take two elements of the incidence algebra, and I want to tell you what's the product that I will have. To tell you what the product is, I have to tell you for every interval what's the polynomial that I am associating. So typically I will write sub st to denote that I am taking the polynomial corresponding to the interval that goes from S to T. So let me write that. So this is poly corresponding to the interval S comma T closed in P. So this is, by definition, the sum over all W that lives in this interval of the polynomial that I will associate to SW times the polynomial that I will associate to WT. Well, once one has this, there's a notion of product and sum and everything on this incidence algebra. This is something that you can actually do over any ring. In case you're familiar with the book of that Stanley wrote, EC1, he does this so he requires this ring to actually be a field, but that's not really necessary. But what you have to have in mind is that to every interval I am associating a polynomial, and I have a way of combining these elements via products and sums. It is not difficult to prove that I of P, so I think I didn't set the notation. This is the name that I will often use. So over is associative and has identity. So there is an element that behaves as an identity in this algebra, and this element is defined by delta ST equals 1 if S equals T and 0 otherwise. So you can check that with the definition that I gave you before. If you take A convolution delta or A product delta, you will end up with A, and vice versa. If you do delta convolution B, you will end up with B. So this is a two-sided identity. And now that you have an identity, you can ask whether some elements can be inverted or not. And yeah, that's something will be important here. Let me, just in case, do another brief recapitulation of Mobius functions and characteristic polynomials. So these are things that you might have encountered in other settings, such as, combinatorics of hyperplane arrangements or matroids, but these are defined for every graded poset. So there's no obstruction to define it now. So another definition, the Mobius function is the element given by mu st equals 1 if S equals T, and this is a recursive definition, minus the sum of all mu SW for W ranging in the interval that starts at S but ends below T. And of course 0, I always require these two things to compare, so it's not defined whenever S is not smaller or equal than T. Since this will be relevant later, let me say something, which is the definition about the definition of Eulerian poset. So a poset P is said to be Eulerian if mu st equals -1 to the row of T minus row of S for all S smaller or equal than T. So whenever the Mobius function is -1 to the length of the interval, the poset is said to be Eulerian. There are other ways of characterizing Eulerian posets, such as saying that all intervals have the same number of elements of odd rank and even rank. There are many important posets that satisfy this property. For instance, phase posets of complex polytopes. Okay, so One more definition, the characteristic polynomial. This is, as I said, something that appears in, especially in the context of matroids and hyperplane arrangements. So the characteristic function is the element chi in the incidence algebra defined by chi st equals the sum over all w in this interval st of mu 0 w times x to the row of 1 minus row of w. So what this is saying is that to every interval st, you are associating the characteristic polynomial of the interval. And by definition, the characteristic polynomial you can think of as this sum where you like collect the sum of all Mobius numbers at a fixed level. Yeah, and I want to emphasize something. I am using like the word function here, for instance, and function here. And whenever I use function, I will be implicitly implying that this is an element of the incidence algebra. And if you say characteristic polynomial of a poset, I will mean that the interval that you are taking in this context is precisely the interval 0, 1, so the full poset. This will happen at some point, so let me mention this now. So in particular, the characteristic polynomial of a poset is just the coefficient of the characteristic function at the interval 0, 1. Okay, so now let us do a recap of Kazhdan Lusztig Stanley functions, which are something that were introduced by Stanley in the 90s in an amazing paper that contains lots of very nice insights. So essentially what Stanley did was define a special kind of functions in the incidence algebra of a poset, and then study their properties and how they encompass various important polynomials appearing in combinatorics. So first of all, there's a special subalgebra. I will denote it I row of P that is contained in the incidence algebra of P. And this I row of P is given by all the elements that lie in the incidence algebra, but having the property that the degree of each polynomial associated to every interval is bounded by rho of t minus rho of s. So I will require that my polynomials are not too long, essentially. And this subalgebra admits an involution. So you can find a nice map that I will denote with an exponent, let's say, rev, that does the following thing. So a rev in ST is defined as AST. Let me put the variable now. So I will take the polynomial AST, I will plug x to the -1, and then I will multiply to the rho of t minus rho of s. So this just reverses coefficients. So the name rev is a shorthand for reversed. So every polynomial appears reversed, but I reverse the polynomials with respect to the maximal degree. So if I have an interval of rank or height, let's say 10, and my polynomial is x cubed, reversing x cubed will be x to the 7. Yeah. Well, now that we have this involution, we can consider a special type of elements in the instance algebra that satisfy a property related to this reversing operation. So this is a key definition by Stanley. Let P be as above. So I have a graded bounded poset, a P kernel. So this is a new notion, is an element kappa in the incidence algebra, in the nice part of the instance algebra, actually, in I row of P, such that, first of all, you have an inverse, so kappa is invertible, and this inverse is equal to reversing the coefficients. So whenever I have an element that satisfies this property, I have a P kernel. And this sounds like a very restrictive condition in the sense that, yeah, here inverting an element of the instance algebra and obtaining essentially the same element with everything reversed seems like lots of equations being satisfied at the same time. And that's essentially correct. But as it turns out, there are many examples that are important and satisfy this property. So let me compile some of them. So examples. So the first example is for all P graded bounded as above, the characteristic function chi is a P kernel. So whenever you have a poset that is graded and bounded, you for free have that this thing is a P kernel. And the proof is not difficult, but it requires some work. So essentially, this is equivalent to the inclusion-exclusion principle in the end. Yeah, so in particular, whenever you have a graded bounded poset, you will have this as a P kernel. Another example is a sort of theorem or alternative characterization of Eulerian posets in terms of kernels. So a poset that is graded bounded, poset P, is Eulerian if and only if the map epsilon, the function epsilon in the instance algebra defined by epsilon st equals x minus 1 to the row of t minus row s for all s smaller or equal than t is a P kernel. So Eulerian posets can be characterized in terms of having this thing as a kernel. And
question, Luis, is that due to Stanley or somebody else?
I think Stanley noticed this first, but I am not entirely sure. Maybe Margaret does know, but I think this was noticed by Stanley first.
Thanks.
Yeah, and one more example, and this is actually in some sense one of the precursors of all this theory. So the R polynomials of all the Bruhat intervals in a Coxeter group. So I am skipping certain details here because I won't deal with this example too much in this talk. But essentially, to a Coxeter group, you can associate a poset that is called the Bruhat poset, and to every interval, you can associate a polynomial that is called the R polynomial. And if you collect all these R polynomials into an element of the incidence algebra of your Bruhat poset, this thing will be a kernel. And the property of being a kernel in this case is more or less tautological because of the definition of our polynomials in that setting. But these are three important examples. There are many more. There's a very nice example that is due to Nick Proudfoot, where he associates to every lattice of flats of a matroid a weird function that is a kernel and essentially is related to the H polynomial of the broken circuit complex. That is a little bit complicated and also requires that one deals with the weak rank functions that I am avoiding here. So yeah, I just want to mention that is also possible. Okay, so this is the basic setup. Now I want to tell you, okay, the definition of Chow function. And to do that, let me just state a lemma. This is so if kappa in I row of P is a P kernel, then kappa st, this is a polynomial, evaluated in 1, is 0 for all s smaller than t. So, for instance, if you take these examples, so the characteristic polynomial, if you take the characteristic polynomial of a non-trivial interval and you plug 1, you will end up summing all the Mobius numbers in that interval, and that will give you 0. Here in this Eulerian example, if in epsilon you plug x equals 1, you will end up with 0. And yeah, this is a phenomenon that happens for all kernels. So if you plug 1 in a non-trivial interval, you end up with 0. So now, definition. Let kappa be a kernel the associated reduced P kernel. So I will modify kappa and obtain something new. Kappa bar in this special part of the instance algebra is defined by kappa bar in ST will be kappa in ST divided by x minus 1 if s is smaller than t. Notice that I can always do this because of the previous lemma, because essentially whenever I plug 1 and my interval is not a singleton, I will be able to perform this division. But when the interval is trivial, I will put minus 1. And yeah, you may ask, well, why not 1? And this is important. This minus 1 is relevant. And now, if you think about it, if you think of elements of the incidence algebra as triangular matrices, as Stanley, for example, does in his book, you will realize that this is saying that you have an upper triangular matrix that has all minus 1s in the diagonal. So in particular, it has determinant that is plus or minus 1, so you can invert the matrix, and you will end up with something that will have polynomial entries again. And yeah, and the idea is that precisely to invert this kappa bar. So this is the main definition. So let P be a, sorry, let kappa be a P kernel. The kappa Chow function is the element H in I row of P given by H equals kappa bar. So this is an element of the incidence algebra obtained by reducing kappa. I can invert it because in my diagonal I have invertible elements in the polynomial ring. And if I do that, I will end up with -1s in the diagonal again. So I want to correct that, and I will put a minus in the end. And let me just in case tell you that it will not be the same to remove this minus sign and remove this minus sign. So this is very sensitive of how you do things. Yeah, this is a Chow function. So in particular, if you are given a kernel, you can ask, oh, what's the resulting Chow function? And I will argue that is relevant because of the 3 examples that I mentioned before. And in those 3 cases, H is very nice. By the way, the notation of overline stands for the notation that people use to denote the reduced characteristic polynomial. So in the theory of hyperplane arrangements, it's very customary to denote the reduced characteristic polynomial by chi bar. So I'm doing the same here. In other sources, such as Nick Proudfoot's survey on KLS theory, he uses the overline for what I denote rev, which is reversing. So one has to be careful when reading articles. But yeah, this is the definition of Chow function. And let me state a general theorem that a general, list of properties. These are basic properties that Chow functions satisfy. The first is that if kappa st is monic for all s smaller or equal than t, then hst is monic for all s smaller or equal than t. Notice that in the 3 cases that I gave you before, the polynomials are monic. So characteristic functions are monic everywhere. The same with this x-1 to the difference of ranks, and the same with our polynomials. So this is just to say that in the 3 cases that I gave you before, we expect that the leading coefficient is 1. The second thing is that if the degree of kappa st equals rho of t minus rho of s for all st, then the degree of h st is equal to rho of t minus rho of s minus 1 for all s smaller than t, and 1 if s equals t. I mean, the degree is, sorry, the polynomial is equal to 1. That's what I mean. So what this is saying is that if your kernel has the maximum possible degree, like in the 3 cases that I mentioned before, for instance, x-1. So in this case, the kernel has the maximum degree, and also with the characteristic function, and you can prove the same for the R polynomials. So in the end, this is telling you that the Chow functions that will arise in these cases will have degree equal to this. And finally, and this is perhaps the most important property, hst of x is equal to x to the rho of t minus rho of s minus 1, hst x minus 1 for all s smaller than t. So this is saying that essentially HST is palindromic. So in particular, in the 3 cases that I had before, I start with a 1 I have the maximum degree and I have palindromicity, so it will end with a 1. So that looks like very suspicious somehow, because I mean, as I mentioned, I mean, as the word Chow is in the title, you can think, oh, this might come from some Chow ring. And as I will explain, in some cases it indeed does. So let me start with the example of the characteristic function. So this is a theorem that that is somehow difficult to prove if you don't know that you are heading towards it. I mean, it's important to know the formula that you want to prove somehow. So let P be graded bounded as usual. The chi Chow function, so I will use the characteristic function as kernel, satisfies HST equal to a big sum. So I will sum over all chains that start at S and go all the way up to possibly T. Sorry, I will fix T0 to BS. So here you have a equal and here lesser equal of this product I equals 1 up to M of X times 1 minus X to the row of Ti minus row of Ti minus 1 divided by 1 minus X. So this is a somehow horrible formula, but in the end, it's not so bad because it tells us a lot of nice features of the characteristic Chow function. Corollary. So just in case, because some of you might be asking how to prove this. So you can prove this, for instance, by taking the convolution of this thing with the reduced characteristic polynomial, and you will end up obtaining exactly minus delta. So that tells you that this has to be the inverse of the reduced kernel. But a way of knowing that you should obtain this in the end comes from a theorem that I will tell you later, that will explain the name Chow. But a corollary that you can see from this statement is that chi-Chow functions are non-negative. In the sense that every polynomial HST has non-negative coefficients. And how does one see that? Well, here in this formula, you have like this 1 minus X to something divided by 1 minus X. So after you cancel out this 1 minus X here, you will end up with a geometric series. Multiplying by X will preserve this non-negativity, products will preserve non-negativity, and summing will, of course, preserve non-negativity. So you have this property. But let me tell you that in general, if you have a kernel, you should not expect the Chow function to be non-negative. So this is a somehow non-obvious feature, if you want. And let me say something else. The characteristic polynomial of geometric lattices, for instance, or distributed lattices, or more generally, Cohen-Macaulay posets, has something called sign definiteness. So the signs of the coefficients of the characteristic function are alternating. So if you know about matroids, you might recall that the characteristic function of the characteristic polynomial of a matroid has coefficients that go plus, minus, and so on. And this H is obtained by reducing the characteristic polynomial and then inverting it as an element of the incidence algebra. So there is a priori no reason to expect that there will be a sign pattern in H, unless there is some sign pattern in chi somehow. But as it turns out, yeah, it's always plus, 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 plus. Yeah, so this is the first statement that you can prove. And now I will state the theorem that will explain the choice of the name. So theorem, let P be a geometric lattice. So particularly it is greater than bounded. Then the chi-Chow function satisfies HST equals to the Hilbert series of the Chow ring of the matroid corresponding to the interval ST. So in a geometric lattice, you have closed intervals that, if you know about matroids, will correspond to a minor of the matroid, and that is a matroid itself. So you can define something called the Chow ring of that thing. You can take the Hilbert series, and yeah, this HST is this, precisely this. And in the context of matroids, the Hilbert series of the Chow ring is called Chow polynomial. So this is Chow polynomial of ST. So there's consistency in the choice of names somehow. Yeah, this is something that holds true for geometric lattices, but for arbitrary posets. So question, if P is not a geometric lattice, can one define an analog of the Chow ring in such a way that the last statement holds true? We don't know. We have tried quite a bit to do it by working with Wagner and Józwiński computation of a Grommer basis for a Chow ring of a geometric lattice using the maximal building set. One can try to play a little bit and try to guess what this has to be, but there's always some detail that make things not work. But let me give you one more striking property that chi-Chow functions satisfy, and that give me the make me believe that if such a ring exists, it should be very nice. So theorem. For all P, so greatest bounded, chi-Chow functions are unimodal. So if you look at this formula here, you see the non-negativity as I told you, but it's not clear that this complicated sum will be unimodal. But yeah, it turns out that this HST is always unimodal. So HST is unimodal. So
Luis, can I ask a silly question? In that sum you had, are those sum ends always like centered at the middle?
No, that's a problem. Yeah,
Right.
yeah. Your summonds are just very crazy. So you cannot. Yeah. But there are other ways of rewriting that formula that will satisfy that property, and you can use some inductive argument that will in the end work. Let me tell you something. In the case of matroids, to prove the unimodality of the Hilbert series of the Chow ring, one often relies on the Hart-Lefschetz theorem. I think that the most elementary proof before this one that would prove the unimodality for Hilbert series of Chow rings of matroids is due to Anastasia with Vic Reiner and Roby Angarone. So in the end, it's somewhat surprising that one can do this combinatorially without relying on any Hart-Lefschetz theorem. And I mean, in the end, I cannot rely on any Hart-Lefschetz because I don't have any ring. So at least so far, maybe someone will come up with the right definition. But my claim now is, if there is a ring, you should expect it to be very nice. Maybe satisfy some form of the Hart-Lefschetz theorem. And let me tell you something else that I find quite interesting. So if P is Cohen-Macaulay, so if you have a poset that is Cohen-Macaulay, then the chi-Chow function is gamma positive. And okay, so just in case, a Cohen-Macaulay poset is a poset such that the order complex is a Cohen-Macaulay complex. Or if you know about commutative algebra, the Stanley-Reisman ring of the order complex is a Cohen-Macaulay ring. Yeah, so Cohen-Macaulay posets are like a very large family. All geometric lattices, all distributed lattices, and many other classes of posets are Cohen-Macaulay. And this is saying that for all of those posets, you have a property that is much stronger than unimodality. So unimodality says that the coefficients grow up to middle and decrease because of palindromicity. I mean, the peak has to be in the middle. But gamma positivity is a much stronger property that says that essentially the coefficients grow very dramatically, let's say. Yeah, it's the proof of this fact was motivated, so related. So the proof is related to a paper by Christian Stump that actually was produced after I gave this talk in Oberwolfach. Christian came up with a proof of something very similar to this, but that is only true for R-labeled posets. R-labeled posets are always Cohen-Macaulay, so this statement is more general. Christian's proof relies on ideas that he had in a previous paper with Galen and maybe Joshua Maglione, maybe I'm not sure, where they define something called the Poincaré extended AB index of a poset. So yeah, and recently there's another paper independently by Xin-Jie Liao. So Liao proved something that is related to this. I mean, the actual statement is much more complicated, but essentially it proves some equivariant gamma positivity for equivariant Chow polynomials of matrix Chow rings, and you can view Liao's proof as related to our proof. Yeah, and let me mention conjecture. Let P be Cohen-Macaulay. Then the chi-Chow function is real rooted. And by this, I mean that every interval has a real rooted polynomial. Real rootedness is much stronger than gamma positivity, and in turn, gamma positivity is much stronger than unimodality. Yeah, mention that there is a prequel of this conjecture that is posed for geometric lattices, which are a particular case of Cohen-Macaulay posets. And for geometric lattices, that conjecture is due to myself and Benjamin Schroeter, and that is also open. So yeah, we expect these conjectures to be very, very delicate because we can prove that the Chow function is a sort of relatively nice specialization of the flag H vector of the poset. But flag H vectors of Cohen-Macaulay posets are something that is presumably extremely difficult to characterize. So one has to come up with a very nice idea to prove this or disprove this. We have some examples of posets that are gamma positive, but are not real rooted. In particular, they are not Cohen-Macaulay because otherwise I would have a counterexample to this conjecture. But they are very, very complicated. So already constructing something that is gamma positive and not real rooted is very hard. Yeah. Now let me use the last 10 minutes to change the kernel now and say something about the epsilon kernel. Okay, so theorem. Let P be an Eulerian poset. So in particular, I can define the Chow function for this poset, but I mean, it's related to what I did before. So let me just consider the other Chow function that will arise from the kernel that is a witness of the Eulerianness of this poset. So let P be an Eulerian poset. The epsilon Chow function satisfies HST equals the H polynomial of the barycentric subdivision of P. Sorry, of the interval ST. So what do I mean by this? So take the interval ST, take the order complex of that, and then take the H polynomial, which is essentially like a transformation of the F polynomial of, or the phase enumerator of that simplicial complex. So I claim that these two things are the same. The order complex is often called barycentric subdivision, so that's why I'm using this terminology. You might ask, is it true that the Chow function in this setting is positive? Question. Prove or disprove that epsilon Chow functions are non-negative. And it turns out that there's a paper by Margaret Bayer and Gabor Hetier in which they construct very complicated posets that are Eulerian and for which the flag H vector is not non-negative. So the flag H vector has some negative entry. But those very complicated Eulerian posets have a positive epsilon Chow function. So let me write this as a note. Note, if there are counterexamples, they must have rank greater than or equal to 7. So they have to be pretty tall. So if they have an Eulerian poset rank 6 or below, well, it's certainly non-negative. And that follows from theorems on the CD index and the flag H vector of Eulerian posets. Notice that Eulerianness and Cohen-Macaulayness are properties that a priori are not related. So Cohen-Macaulayness will always imply positivity because Cohen-Macaulay posets have non-negative flag H vectors. And yeah, and if you have a non-negative flag H vector, you will have certainly a non-negative H polynomial of the various index subdivision. Now, let me tell you some counterpart theorem for the gamma positivity and the unimodality that I mentioned before. Theorem. This is essentially due to Calle-Carew. I mean, I will skip mentioning the CD index and so on, but this follows from Carew's work. So if P is Eulerian and Cohen-Macaulay, some people call this property Gorenstein star. So Eulerian and Cohen-Macaulay means Gorenstein star. Then the epsilon Chow function is gamma positive. So the proof is short once you know this result by Carew on the CD index. So essentially HST, so the gamma polynomial associated to HST equals a positive evaluation of the CD index of ST. Yeah, so Carew proved that the CD index of any Gorenstein star poset is non-negative, so this gives you the result. And there is a conjecture that should be attributed in the case of polytopes to Brenti and Velker. And in more generality to Athanasiadis and collaborators. I mean, he has written various papers with different people, and in all of these papers, there's a mention of some form of this conjecture. If P is Eulerian and Cohen-Macaulay, the epsilon Chow function is real rooted. This is very open. This has been proved to be true in the paper by Brenti and Velker, but only for phase posets of simplicial polytopes. So phase posets of polytopes are Eulerian and Cohen-Macaulay, but there's still a huge leap between those two classes of posets, and more so if you restrict to simplicial polytopes only. And the proof relies on a very nice result of Peter Branden on certain transformations that preserve the property of being a polyfrequency sequence. And yeah, this is a sort of analog of the two statements that I had before. And let me not tell you more let me not mention in detail the case of R polynomials and so on, but we have a similar theorem. Let me call it theorem. It's not quite a theorem because it depends on another conjecture that people expect to be true, but the Chow function that will arise from R polynomials is expected to be gamma positive. The actual conjecture that will imply this is a conjecture by Villera and Brenti on the non-negativity of the coefficients of the complete CD index of a Bruhat interval. And also for those experiments suggest that there's real rootedness. So in the three settings that I mentioned, if your poset is sufficiently nice, namely Cohen-Macaulay and has the corresponding kernel, the Chow function that arises from that kernel is presumably real rooted. And yeah, we have run various experiments, and we also introduced two additional functions that are called augmented Chow functions, and we believe that in the case of matroids, the Chow functions, the augmented Chow functions will be nice, but in the other cases, we have no clue of what's going on. For instance, we do not know what are the augmented Chow functions of an Eulerian poset. And I think that there's room to do a lot of things here. I mean, we decided to include various open problems in the paper. Right now, I don't have time to enumerate all of them. There are quite a few that I already mentioned. But yeah, among the ones that I include in this talk, I regard the problem of finding an analog of the Chow ring for arbitrary greater bounded posets as perhaps the most intriguing one. And also this question on the positivity as a very nice project to run computations. I think that the best source for this question is the paper by Bayer and Hetier on complicated flag H vectors of Eulerian posets. But let me also tell you that Stanley in EC1 has an exercise labeled with a 3, which in that scale means like extremely hard, asking for an Eulerian poset with a negative entry of the flag H vector, which is essentially the content of one of the examples in the paper by Bayer and Hetier. So this is expected to be harder than that problem. But I don't know, maybe someone with some insight and some powerful computer can come up with an example. I would be very happy to know about this. Well, that's all, and yeah, thank you.
Thank you, Luis. Do we have any questions?
Can I ask a couple of small questions?
Mhm.
Hi. So, yeah, I guess I'll just ask a couple of random questions. So going back to your conjecture about the Chow functions being real rooted, did you notice any like interesting patterns in the examples you've considered, like geometric lattices and so on, of like the interlacing sets?
Well, so there's a theorem that I'm hiding here, which is how to write the Chow function as a specialization of the flag H vector.
Okay.
So the flag H vector contains much more information. It contains information about all flags.
Right.
But it turns out that you can extract, from special coefficients, the full Chow function. And Cohen-Macaulay posets cannot have random or very ugly flag H vectors.
Okay.
So I guess that my pattern would be like, yeah, since flag H vectors of Cohen-Macaulay posets are nice, I might expect Chow functions of those posets to be nice. Yeah.
I see. All right. So my second question is going to Caruso's on the Gornstein star poset on the CD index. So I guess you're referring to that paper where you use like intersection cohomology stuff, etc., right? Do you I mean, this is like sort of just kind of maybe not a sensible question, but do you see maybe like a possible, like maybe your technique do you have any idea if your techniques would help like with coming up with a more combinatorial approach to the negativity of the CD index in this situation?
I am not sure, but
Okay.
there's a previous paper by Stanley in which he proved the non-negativity of CD index for, among other things, phase posets of polytopes. Maybe, I don't know, maybe one should take a look at that instead.
Okay.
But yeah, I'm not sure about what's the answer to your question.
That's okay. Thanks. That was it.
Any other questions? Great.
I'm not sure, maybe the question was implicit in Suyun's, but with the Chow function of the Cohen-Macaulay poset, what gives you the courage to conjecture that's real rooted when the geometric lattice case is still open?
Because, okay, so sometimes I have seen instances of certain conjectures being posed for a restricted class of posets, in this case, geometric lattices, but that is misleading somehow because you want to use the structure of a geometric lattice. And maybe that's not what you have to do. Maybe if you go to Cohomological and you just try to understand the behavior of the special entries of the flag H vector that appear or contribute to the Chow function, you can somehow prove all the properties such as low concavity or perhaps real rootedness. And yeah, and we felt encouraged to include it also because the analog, the augmented conjecture, so the rearness of the Hilbert series of the augmented showering seems also to be true, and interlacing seems also to be true. So it doesn't seem that there's any, I mean, you don't get worse just by thinking on Cohen-Macaulay posits, not at all. So maybe that's the right setup to do this.
Convincing. Yes, thanks.
Yeah.
Any other questions? Then let's thank Luis again.
Thank you for attending, and yeah, please, if there's any follow-up questions, feel free to email me, and I would be glad to discuss about this with any of you. And again, thank you for coming.
And just a reminder that I think our next talk is on December 6th.
December 4th. It's a Wednesday, right?
Okay, yeah, it's a Wednesday.
Yeah.
The usual time and place. Okay, thanks again, Luis. See you guys.
Thank you, Graham. Thank you, Christine and Ahmed. Bye-bye.
See ya.